Hello and welcome to this webinar of Copernicus Climate Change Service Energy. My name is Alberto Troccoli. I'm the coordinator of the C3S Energy on behalf of ECNWF, who's implementing this service on behalf of the European Union. It's a pleasure to hold this fourth webinar. We've already discussed some of the results in previous webinars, so I invite you also to go back to those. They are recorded and available online. We'll provide the details later. And this one will focus on two case studies that use C3S Energy data to showcase how the data could be used in practice. I'd like to also acknowledge the contributions from our partners, Armin and Eberos, NL, and ADF for the great work and collaboration on this contract. As an overview of what we've done, I've just touched briefly on the essence of the contract. It's a standard slide which show how we transform climate data into energy indicators for PV, solar power, wind power, onshore, offshore, electricity demand, hydropower generation, run-of-river and reservoir. And we do this for three streams: historical data from 1950 to present, seasonal forecasts, and projections out to 2100. And we are in the process now of also moving from the current European service, so covering the European domain, which is operational, to the global version in 2025. We'll hear more about the service in the first talk. And before we do that, just some information about the webinar. So the audio and video are deactivated by default. That is your audio and video, not mine, and not the speakers. And then you can submit the questions in the Q&A section. We will address them verbally after the presentations, but we may also respond to them in writing during the webinar if time allows. So you're invited to submit your questions at any time through the question and answer tab. The webinar will be recorded and will be available online. And the agenda is the following. So this is webinar 4, like I said, and it's about the case studies, the two case studies. We'll start with an introduction by Nube Gonzalez-Reviliego, and then we'll go to the case studies, the two case studies, and in between we also do a quick poll to ask some simple questions which are useful for us also to know your interest, your goals with C3S data, how you intended to use it and so on. We'll see that later, but without further ado, I'd like to introduce now the first speaker. Like I said, is Nube Gonzalez-Reviliego, who is the Energy and Agriculture Technical Officer of the Copernicus Climate Change Service at the European Center for Medium Range Weather Forecast, ECMWF. And she has a PhD in climate and extensive experience in co-developing and implementing climate services for different sectors, including renewable energy, agriculture, health, with both private and public institutions. She has participated as a climate service scientist in many national and European projects and is currently involved in the operational service of C3S Energy sector. So I'd like to hand over to Nube for an introduction on the C3S operational service. Thank you, Nube. Over to you.
Thank you, Alberto. Would you please stop sharing so I can do? Yeah, so I would like to join. Let me share. Okay, here we are. So, yeah, first of all, I would like to join Alberto in welcoming you to this series of webinar for the energy sector. As Alberto mentioned before, this is the fourth webinar that we are doing. The first one was about talking about climate indicators. And then the second and the third webinars were about the energy indicator that we are providing in the service. So I invite you to go into this website, into the C3S webinar for seeing the recorded if you are interested. And let me start for those who don't know what is about. Copernicus Climate Change Service is one of the 6 services within the European Copernicus program. Copernicus is the Earth observation component of the European Union Space Program, and its main aim is to develop European services based on both satellite Earth observation and in situ data. The Copernicus Climate Change Service, the main mission is to support society by providing authoritative information about the past, present, and future climate information in Europe, but also all over the rest of the world. If I have to say what is the climate change service in a nutshell, I will highlight that we are providing open and free of charge climate data set. All the climate information that we are providing is fully documented. And also you can find a full traceability of the information. Also, we offer quality information of the data set that we are providing that is assessed by independent experts. And also within the Copernicus Climate Change Service, we aim to showcase how different sectors use different Copernicus services. But well, regarding today, I would like to briefly explain what we are providing in the Copernicus Climate Change Service for the energy sector. So right now we have this operational service for the energy sector in which we are providing 2 main data sets in which we provide climate and energy indicators over Europe for the historical period, and they are derived from reanalysis. This data set is operational, which means that we are updating it in a monthly basis. Every month, you have a new data in place. But also, we are providing climate and energy indicators for the future till the end of the century. And these indicators are derived from climate projection from Eurocordex climate models. These data sets that we are providing at the C3S operational services provide free and quality assured data that can help the energy sector in several decision making, but some examples could be identified optimal site with the historical data set, also planning the grid extension, maybe for the future, also assessing potential yield, because we are providing not only climate information, but also energy indicators, also allow user to adapt to adverse climate conditions, but also, of course, many other applications. But what I would like to highlight today is that this operational service for the energy sector is being expanded. And we are currently working in providing not only these climate and energy indicators for Europe, but we would like to expand it to provide them at a global scale. Also, we are enhancing the energy modeling behind each of the energy indicators. And we aim to produce not only historical and climate change projection information, but we would like to add a new layer that is the seasonal forecast component. This seasonal forecast component will be also operational and will be updated monthly. These new global climate and energy indicators will be available, I will say, during next year, hopefully more or less during the first quarter. So you will be able to find it here. This is our webpage. You can go here, and this is the operational services for the energy sector webpage. You have the QR here on the top right of my screen. Also, in the expansion of this C3S energy service, we are also working in comprehensive documentation of the energy data set, but also we would like to deliver training materials, such as, for instance, Jupyter Notebook for those users that have a more technical background, let's say, but also some e-learning module on energy for those users that have less technical expertise. As well, we are aiming to create a web application for visualizing all the climate and energy indicators that we are providing within the energy service in the 3 temporal stream. And of course, the idea is that a user can have a first taste of the data set before downloading the data, and also they can explore how they look like in the future, maybe, for instance, and help in the decision making. But also in this expansion of the C3S service, we are currently working in 2 case studies. These case studies are the ones that my colleague will be presenting you today. And one of those is how to use a seasonal forecast to develop a gas demand model. And this case study has been done by Enel. And then my colleague will explain you in more detail in a few minutes. And then the second case study is developed by Everose, and they use the climate change projection as a key element in developing solar project and finance. But even though these are the 2 case studies that we are currently developing, there are some other illustration on how to use the data set provided in the Copernicus Climate Change Energy Service. And you can find here in the data in action below C3S webpage. Here is the link where you can find this globe, and then you can filter by sector, and you can discover some other case studies that can illustrate on how to use the climate information that we are offering for the energy sector, but also for some other sector. And I think I will stop here. I just would like to wish you a nice webinar. And if you have a question, please just ask in the question and answer chat. Thank you very much.
Excellent. Thank you so much, Nube. That was a very good and succinct overview of the C3S offerings, which is expanding, improving, and so on. So keep watching the space. So like I said before, I promised you that you would have your opportunity to interact with us now through a poll. So before we move to the presentations on the case studies, we'd like you to interact with us through this poll that you see now appearing, so you can start to respond to the questions at your own pace, but I will also read the questions to help the people also who like to hear them in verbally from me. So we'll take about 5 minutes to go through the poll. And again, I invite as many of you as possible to respond, please. So the first question is, how familiar are you with the C3S Energy Service and its data products? So you can only have one choice here. From very familiar, somewhat familiar, slightly familiar, not familiar at all. Okay, so that's easy. Second one, what is your main objective in attending this webinar? Again, one option, learning how to use seasonal forecast in energy strategies, understanding how climate projections can improve energy planning, networking and engaging with experts in the energy sector, gaining insights into future trends in climate and energy. So like I said, I'm afraid it's only one option. You might have more than one. Choose the most relevant. I don't know if there is space. Yeah, at the end, there is actually space for some text. So if you like to also refer back to this question, adding other objectives, please type them at the bottom. You could say also all of the above at question 2. Sorry, I think we should have had the option for all, but never mind. Number 3, which temporal resolution do you think are the most relevant for your work with climate data? Please select all applicable. So hourly data resolution, daily, weekly, monthly, annually. Here you can choose as many as you like. Number 4, which type of climate data is most important for your work or area of study? Again, here, one option, historical data to analyze past trends and variability, seasonal forecast to plan for the immediate future, and future projections to assess long-term strategies and impact, as well as I'm not sure. And number 5, last question with no text is, do you plan to use C3S energy datasets for your work? So the first answer is yes, I'm already using them and I'm planning to use them in the future. Or no, and again, I'm not sure. And the 6th question is to add a bit of text, particularly around the type of application, decision-making you intend to use the data for. If you could please write some indication here, again, would be very useful also to guide us through the next phases of C3S energy. Right. So we'll leave you 1 minute to complete. Also, if you have anything more to add, you can use the Q&A. And I would now move on to, very good, thank you very much. We achieved more than 70%. Thank you very much for your input on this. And let me share again the screen and show you the agenda as we move on to the case study now. First case study 1, around the use of seasonal forecast for predicting gas demand. And this is presented by Dr. Laura Mariotti together with Luca Sapienza, both from Enel. And while the speakers prepare, Laura prepares for her presentation. I briefly introduce Laura and Luca. So Laura is a meteorologist at Enel Global Trading since 2021. She has a PhD in the degree of physics. Her studies were focused on climate change, regional climate modeling, hydrology modeling, and in C3S Energy Service. She's involved in a case study that will be presented here using ECMWF seasonal forecast for gas demand in Northwestern Europe. Luca Sapienza is a quantitative energy market analyst at also Enel Global Trading. Since 2020, he started his career in Enel in the fundamental market analysis team, where he focused on the European power markets, managing price forecasting models, developing gas demand forecasting and monitoring, and power market fundamentals. He's now focused on the gas markets, where he monitors and models the European and global gas markets together with Steam. And C3S Energy is involved also in this case study, as we will see. So it's a pleasure to have both Laura and Luca present the case study one. So over to you, Laura, first, and then Luca later. Thanks.
Thank you, Alberto. Good day, everyone. So we start with the case studies one. Enhance gas demand modeling through seasonal temperature forecast. We start with a small introduction about Enel, the problem that we are going to study. So Enel
Sorry,
is
Laura, can you share the slides, please?
I shared, no? Okay.
I don't see them. Let's try again.
Can you see now?
I don't know if others see them.
Can you see my
Okay,
screen
they're
now?
coming. They're
Oh,
coming.
sorry.
Yes. Okay, yes.
Sorry. So as I told you, we start with a small introduction about Enel and the problem that we studied for this case study. So Enel is a multinational with a worldwide presence. We start in Italy and now is present in 28 countries. And has a many portfolio like power and gas. Is also focused on the renewable generation, such as solar, wind, and hydro. And on Monday, there was the Capital Market Days from the company, and where the chair explained all the plans for the future of the company. And he confirmed one of the main goals of the company is to build the future through sustainable power and to be carbon-free within 2024. However, this exposed the company to a lot of risk in the market, and that is why we are here in this European project. So the main goal of this case study is the gas demand forecast for business over the Northwest Europe. And to do this, we will use the seasonal temperature forecast provided by ECMWF. The power and the gas demands are strictly related to the temperature. There are two main impacts. One, directly from the temperature for the demand of power impact to the gas demand, like in summer or in winter. For example, the heating, when it's cold, there will be a peak. And another one is indirectly from the temperature due to the renewable generation. If we have a strong renewable generation, like wind and solar, typically the old generation of fossil and gas are turned off. So the gas demand could be lower and as an indirect effect from the temperature. So this is quite complex, it's non-linear, and this is a very simple scheme. The demand has an impact also on the price, because the price is a relation on the demand and the availability, and also on the volume. So if we have a strong demand, we have an higher volume. And this is not completely correlated. Basically, we have two variables in the problem. One is the volumetric risk, and the other one is the price risk. The margin is the product of these two variables. This is a risk from the weather. So the ability to know in advance what kind of weather we can expect will provide us an important advantage in the market. For the reason, we need to have a good weather forecast in order to optimize our portfolio of gas and also indirectly the power portfolio. So this is a general overview of what we have done. So starting from the weather and data and also some economic data, we use an industrial gas demand to try to establish a relationship between the environmental variables and the demand. Then, with a model of price of market, we try to estimate the prices and the volumes to have an exposition to the risk of the market. The key point is to provide proper weather data with a time horizon of typically from 6 months ahead up to 2 years. And for the 6 months, we start to use the seasonal forecast, the CIS5 provided by the ECMWF. Look at the top left panel graph. In the last 3 years of the temperature are reported. We can see that the temperature are very different from the normal values, and the strong deviation from the normal can affect so much our demand forecast. This is the main problem for us. Moving to the right, the top right, we see the relationship between temperature variation and demand variation for the Northwest Europe, the green area, during the winter about the residential gas demand. As we can see, the relation is very strong. When we have a spike in temperature, we have to expect a spike in consumption. Before the project, for example, we could predict some cold spike because we use only fixed temperature values in the gas model. Moving to the bottom chart, so you can see that to make the different scenarios, we are able to do some different scenario in order to take in place all the possible deviation from the normal expectation. First, we are to do a first prediction, use the normal or the average temperature, and then we are to apply some stress and temperature that can lead to different results in the demand. With this, we were able to estimate the range between the minimum and the maximum that is very important from us. The goal is to narrow this difference to reduce the impact on the demand. To do this, we have to improve the quality of the weather forecast. This is the concept of the project. We focus in the area of the Northwest Europe. With temperature, we use the C5 6 months in the future. And the model is now, we tested for the past, but now is working operationally. Before the case study, we used just 12 values as normal values for the project, for the gas model. Now we were able to use all the 51 members of the CIS5. And what we have done is to use like a Monte Carlo approach. We use the 51 members from the weather as an input to the gas model. So we run 51 times the gas model, and then we are to make 51 of the market model. In this way, we will have a real distribution of the market prices current with the weather scenario. We will use this real distribution also for sensitivity tests that are current with the weather forecasting. So we had also the possibility to analyze the performances of CIS5 that are produced every 6 months with the 51 member with an horizontal resolution of about 36 kilometers. We compared CIS5 with the ERA5 area analysis, always provided by CWF. We start with the statistical analysis of the error associated to the forecast produced by the CIS5 to see how CIS5 can improve the tendency of can reduce the tendency of the temperature. We calculate the correlation, reducing square error, also the BI. Here we reported just a few charts. These are the correlation from January, April, July, October for each state that we are working. What we in general see that CIS5 show a good correlation index for the lead 0. For the lead 1, the correlation is quite good in April and October, and is lower in January and July. So this suggests us that the model is performing better in springs and autumn. The variability of the forecast decreases significantly after the lead 2, and they become really a third of the ERA5 ones. These results are also confirmed with the root mean square error. Here just reported the root mean square error for the space. We also calculate the MAE. The things that is making it notable is that regardless of the run months, January is the month with the higher root mean square error. And the months the MAE confirm this. So in this one, as the worst forecast, especially in Germany, the green light bar. And instead, for UK, the root mean square error, also the MI indexes, are systematically quite lower and respect to the other country. It's the green light, dark light, the dark green bar. And this suggests us this UK, the performance are quite better. And probably a possible explanation of this effect could be that the westerly Atlantic flows is easier to be forecast with respect to the more chaotic circulation present in the European, in Central Europe. We also had tried to answer the questions, do the C5 forecast present in the the real variability of the weather? So what we analyzed from the ensemble mean, from all the ensemble mean of the project, we calculated the sigma of CIS5 and compare it with the ERA 5. We had the confirmation that of our hypothesis was right, so the forecast temperature CIS5 are less variable than the actual temperature 5. And a possible solution in case of this significant difference of the variance is to apply the technique of the quantile mapping for the temperature, and we are still working on that. So now I can leave the room to Luca for the gas model. Thank you.
Thank you, Laura. Yes, moving ahead with the gas demand model. If we go ahead with the chart, okay, thank you. So the first point is to select a model that we are going to use to forecast the gas demand in Europe, and we focus on seasonal ARIMA model with external regressor. Then we decide to change the input temperatures variable that have been used in past that were taken from an external provider with the one of the ERA 5, allowing us to use the ACMWF scenarios for the future. Furthermore, we decide to include some other external variables in order to reduce the forecast error for the gas demand. And finally, we perform, as Laura told before, a sort of Monte Carlo simulation running simultaneously all the 51 scenarios for each month. So if we go ahead with the chart, as I said before, we focus on a seasonal ARIMA model with external regression in order to forecast the European gas demand. The European gas demand can be divided into 3 sectors. And we have the residential demand that obviously has a strong seasonality, and then the other 2 components, the power, the gas for power demand arising from thermal generation, that obviously is related to the dynamic of the power markets, and industrial demand. For all the 3 components, we developed and we estimated different models that are run simultaneously, and all the 3 different sectors have different external variables. For the residential demand, the main driver is obviously the temperature, particularly relevant during winter months instead of summer. For the power sector, we use as external variables the tightness, that is an indicator used in the power markets that basically describe how much the power market is tight. So is a difference between the consumption, the power consumption, and the renewable generation in nuclear production. So it tells us which is the space remaining for the thermal generation and therefore for the gas generation. Finally, the industrial demand, that is related both to temperatures, but also to some macroeconomic variables such as the industrial production. And here we can see the backtest that we performed, the in-sample backtest that we performed for the gas demand model. In particular, in this case, we are assessing the improvement that we obtain from switching from the old temperature provided by the external provider and the one provided by ERA 5. So you can notice just changing the input temperatures, we obtain a small reduction in terms of forecasting error. And we can see it better in the auto-sample of analysis in the next chart, where we try to yes, Laura, thank you. If you can go, thanks. Where we test the performance of the model out of sample. So we run a different forecast with a different input variable. Namely, we used the 5-year average as input as better forecast for the temperature, and then we decided to use the median of the ACM and WF 51 scenarios, the median for each month of the 51 scenarios. As you can notice, the median of the CMWF 51 scenario seems to lead to better results if compared to a simple 5-year average. In this case, we decided to use the 5-year average because the normal values, so the longer term normal, would have been lead to higher error due to the higher temperature that we are observing during last years. So in particular during the winter, so in the Q1, the reduction in terms of error is very strong. This thanks to the median of the ACM-WF 51 scenarios, leading to reduction in terms of both of MAPE, but also in terms of nominal value. So in this case, in BCM, billion cubic meters of gas. And this is much important for us since also 1 BCM could lead to a very strong change in gas market prices. Furthermore, we also analyzed the scenarios arising from the different 51 scenarios of the CMWF, both in terms of temperatures, but also in terms of results, so in terms of gas demand. As you can notice, both the temperatures and the gas consumption have a distribution that is somehow normal, but or maybe loco-normal, and obviously the relation is asymmetric. So we can have some extreme values, such as for in this case for January 24, some extreme negative values that could lead to extreme scenarios in terms of gas consumption. And this is very important for us, since we can use this distribution in order to perform a sensitivity analysis using the percentile of the temperature distribution, and therefore the percentile of the gas consumption distribution, in order to stress the European gas market with our fundamental model, in order to analyze the impact of these temperatures on the demand, and therefore the impact on prices and the global and the European system. Going ahead, we can see here another representation of how the scenarios are used in terms of gas consumption. And obviously, in the table before, you can notice how, for instance, the temperatures, the minimum temperatures were pretty strong in terms of difference from what is a mean, and therefore this led to a strong increase in gas consumption. For instance, in January, we can see a minimum temperature of minus 1.4 degrees that lead to a demand of almost 10% higher if compared to the mean. And this is a big stress for the European gas market, in particular in the winter and in this period. Finally, all this work has been developed through the use of RStudio and Python, and we decided to develop a Shiny dashboard that is actually working, both to analyze, as you can see from the bottom right, the scenarios, so arising each month for the 51 scenarios, analyzing the distribution, and in order to better understand what we are using in order to predict the gas demand, and also to run and analyze the demand arising from the developed model. Finally, we can go to the conclusion. Thank you. So the use of the CMWF scenarios have been used for developed a gas demand model in order to forecast the gas demand. Then the CS5 shows a good correlation indexes for delete 0, but from delete 1 the correlation is lower. The CS5 seems to perform better in spring and fall, while the performance is worse in winter and summer. And finally, the variability of the forecast decrease after delete 2 and become roughly 1/3 of the ERA 5 However, the use of the CMWF 51 scenarios lead to a significant reduction in terms of error in forecasting the European gas demand. Obviously, this compared to the use of normal or shorter term average. Furthermore, the possibility to run different simulation based on the different scenarios provided allows us to perform, as I said before, sensitivity analysis that are quite important in this moment, since they allow us to evaluate the impact of extreme scenarios on the European gas market, and this is particularly relevant during the winter season. So thank you all for the attendance.
Thank you.
Excellent. Thank you very much, Laura and Luca. That was very comprehensive and on time. And I expect we'll have several questions. We already have one, but please, everybody try to submit one question each. We won't be answering all of them if we get one each, but yeah, it would make quite an interactive webinar. So we'll look forward to your questions. So submit them as we move on to the next presentation for case study 2. So we have now Nicolas Scholler from Everose presenting case study 2 on the use of climate projections for the financing of solar power plants. I'll let Nicolas load the presentation, and while he does so, I will introduce him. So Nicolas is a multidisciplinary engineer with experience across solar photovoltaics, storage, and hydrogen. Nicolas' expertise encompasses product development and certification, project design and performance assessment, technical and commercial due diligence. Nicolas has been involved in renewable energy since 2006. His experience includes a great variety of projects and technologies, from rooftop systems to large floating PV systems or hybrid PV plus BESS installations. And recently he has managed the due diligence of several standalone grid-scale storage projects. Nicolas is currently a partner at Everose, an employee-owned consultancy specializing in renewable storage, hydrogen, and wider energy flexibility. And it's a pleasure to have Nicolas here with us to present this case study. So over to you, Nicolas.
Thanks so much, Alberto, for the introduction. So just a bit of logistic, making sure that you are seeing my screen.
All good. Yes, you're ready
Okay.
to go. Thanks.
Excellent. Let's crack on then. Well, first of all, thanks a lot for this opportunity. It's been quite a journey for us. So the contribution is very modest compared to all the tools developed by Copernicus, but it's been really enjoyable. So I hope this presentation will reflect the interest we've had in this case study. So I will say a few words about Everose. Then I will spend a bit of time in trying to explain what is our role as technical advisor, and more specifically on the importance of the energy yield assessment for project development and financing. So I will detail a bit how we work, what tools are currently used by the industry, and then I will present more in detail the case study itself, how we use the data, what were the results that will lead me then to the conclusion. So let's move on rapidly. So, well, you already did the introduction. Everose is a technical advisor. We are employee owned. We are offering a wide range of services. Basically, the core of our activity is what we call due diligence. It's generally requested for precisely project finance, but we can provide support at different stages. At early stage, it can be more strategic support, market development, can be more specifically on technology. And as the portfolio project advance, we can help also our clients in more operational support or after completion in performance monitoring, in claim management, etc. And ultimately in life extension. So when you develop a wind farm or a solar farm, you've got generally an original lifespan of about 20 years. And at the end of this period, you might want to continue with your asset. Okay, so what about project finance? How is it done? So I'm not a financial advisor. I'm not going to enter into details of senior debts, breach, etc. But give you a nudge of what it is from our perspective as a technical advisor, what it is important. So when you talk about future projects, so again, our focus today is solar, but would work pretty much similarly for other renewable energies. So you will start with the project developer, we call generally sponsor, and this sponsor has an idea, has big plans, but nothing can happen without funds. So the sponsor will go to the lenders, and most of the time the lenders then will ask us, technical advisors, so it can be Everose, but we have competitors, to support. And basically the role of the technical advisors to be in between the project developer and the bank to assess the viability, the durability, and expected profitability of the project. So obviously, to assess the future revenues, the energy assessment is important, but clearly it's not the only subject to be handled by the project developers. I won't enter into details, but if you want to develop a solar project, you have to take care of many different considerations. Obviously, the energy assessment is an important parameter, but it's only one of the so many things you have to consider. And unfortunately, project developers are not climatologists, which leads to some misunderstanding. And it might sound weird or silly to most of the audience, certainly if you have some expertise in climate, but we have been confronted, and that was the original discussion before we started working on this case study. Very often our clients will claim that we are very conservative because in the future, because temperature will rise, we will have more sunshine. So it should be good for solar, we will have more energy. Well, the truth, and that's what we pretend to have explained in the following presentation and the case study, is that there is no direct correlation between temperature rise and rise in solar resource and solar generation. So a few words about the tools, how we work, and the concept of P50, P90 generation, which are key concepts. So rapidly, why the energy yield assessment matters? Well, it matters at early stage development of the project, because before you even consider putting a single module in the field on the roof of your building, you will need to have an idea of how much energy you can generate. So at the development stage, very early, you will need to have a reasonably accurate yield assessment. The closer you get to construction, as you proceed with permitting, with contracting, etc., you will need to refine your assessment, because ultimately that's the figures you will present to the bank that will, in part, determine the way you get your project financed. Then when you enter the construction phase, so during the construction itself, obviously the yield of the future project is not that important, but at the end of construction, you will have a trial run. And very often also after commissioning, for 2 years, you've got a warranty period related to the construction contract. And one of the parameters will be comparing, benchmarking the actual energy production against your model. So for this step, it's also very important, because it can lead to important penalties. If for some reason the contractor did not build what you purchased, you can claim a lot of money as a compensation. And then obviously during the operating life of the project, it is also important to have in mind this original model, because over the lifetime, you may need to monitor the performance also, because most certainly if your tariff, for instance, is for 20 years, you may have negotiated also a loan for 20 years, and every year you will have to demonstrate that your asset has been performing well, and you may need from time to time to come back to your original simulation to prove that it is up and running as expected. So to build this model, you need a simulation tool, and this is the tool we've used for the case study, PVSYST. So it's a software originally developed by Professor Mermou from Switzerland, Geneva. And it's quite impressive, because I think it's still very little team, PVSYST as a company now. I think it's a team of 10 people, and you've got hundreds, thousands of projects that have been financed based on PVSYST simulation. So it is de facto the industry standard. And you see, I've highlighted it is a bankable tool, which means that if you go and discuss with people in the industry, and in particular banks, and you present simulation with PVSYST, well, you're already opening the door, because people understand that PVSYST is a reliable tool. And that's why we thought it was important to use this simulation software for this case study, because the results we had to analyze were processed by a software that is known, that is very accurate, that allows to adjust a lot of parameters, and which is very often used to benchmark any development. So it's quite a robust tool, and it has a proven track record. Then obviously, because we are talking about solar, we need to know the irradiance. So current practice is to use data generally based on satellite imagery. And you've got a few providers that provide a ready-to-use file that you can input in your PVSYST or other model to run your simulation. Again, it is important to have bankable data providers. So there are a few players on the market that are recognized. Same point, you may come with very accurate weather data, but if you come out of nowhere, you don't have track record, that will lead to a lot of discussion to convince your lender that the data is valid. And technically, we can generate many years of weather data on historical data, or as we did for this case study, we will detail that a bit further, future data. But for many reasons, one of them being time and obviously money, we generally use a typical meteorological year, which is, as illustrated by this graph, some kind of Frankenstein year. So we will extract from the period of time for which we have available data, so very often more than 20 years, the most representative of the median scenario. So we then generate one single file, and that is this file that is used to run the model and to make the assessment of the energy generation. Which leads to the concept of P50 and P90. So I'm not a statistician, but it's just an illustration. The P50 would be the median scenario, and P90 is slightly more pessimistic. So how it works, and I will come back to it towards the end of this presentation. But basically, you take your system design, your TMY, you process it to generate a model with a series of loss factors and consideration for the piece of equipment you will have in the field. This will give you a P50 scenario, which is generally the base case used by the sponsor to assess the profitability, the future profitability of the asset. And then, because the lenders want to be safe and want to guarantee that you will pay back the money they will loan you, they will ask you to consider a more pessimistic scenario. So that's the P90 you saw previously on the left on the bell curve. So to get from the P50 to P90 scenario, we apply some uncertainty factors that are related to the model. So mainly PVsyst. It is still a model, it's not the reality. So you can expect some discrepancies between the model and the real life, and uncertainty on the input data. So here the question is, given the perspective of climate change, could it have an impact on the P50? So is the resource for a project is going to change significantly? And then if it changes, will it also impact the P90 by increasing, decreasing the variability, the uncertainty, etc.? So those are questions we try to answer on the case study. So now, finally, I will talk more in details about how we worked and what were the temporary conclusion we can present today. So it is important to understand that, well, I mentioned that sponsors are not climatologists, but we either. And so we needed some period of time of adaptation to understand what kind of data we could get. And so the original phase was focused on one asset in Spain. It could have been any territory in Europe, but we thought also it was important, and I will detail that a bit later, to consider real assets. So we picked projects that are already in operation, so we could potentially benchmark the simulation against the real operational data. So the first work was on this Spanish asset to just understand in what format we could get the data, how we could process it, if we were able to work with those data in PVsyst and what results. Then we decided to go further, and the idea was also, as Nube mentioned, to go outside of Europe to see that the service could be useful not only for the European countries, but and other geographies. So based on our available data, we had to limit ourselves to 2 African countries, but Egypt and Senegal present very different climates. So we think that it's still interesting because we could cover very different situations. And ultimately, so all those data were originally based on monthly or daily values. And for Spain, we could get higher resolution hourly data because I did not mention, but PVsyst will use hourly generation. So if you input monthly data, PVsyst has an embedded algorithm to generate hourly data, but it could introduce some biases. So we wanted to check if by inputting directly hourly data, we could see differences in the results. And rapidly on the metrics we used, so we are talking about energy yield, which is basically the energy you can get from every kilowatt peak of modules installed in the field, and the performance ratio, which is the ratio between the energy you are injecting to the grid and the DC maximum theoretical energy you could get. So before all the conversion, because obviously PV modules are producing in DC and the grids are in AC, so you need the inverter to make the conversion And obviously, with every conversion, you got losses. So here, rapidly, the 3 projects. So as I mentioned, so the Spanish one, and then the 2 projects in Africa. Well, the details are not super important here, but again, I want to stress again the fact that those are real projects. So it was interesting to work on those models, because we know that those models are representing real life, and so they are realistic. So the synthesis of stage 1, so we had a lot of data to analyze here. We are illustrating, so we received data for 9 different models. Then we decided to focus only on one of them. So we picked CAMS, which is one of the models that was made available to us. We had past data, so starting in 1950s, I think, and then forecasted data until almost 2100. So as you can see on the graph for different metrics, so I'm afraid it's not super clear, but we have the global horizontal irradiance temperature. Those are the 2 input parameters. And then on the right, the evolution of the performance ratio and the evolution of the yield. That was for the Spanish side, so interesting. And we will see that with the other data set, we got similar results. So the evolution is clearly increase in temperature, more or less pronounced, depending on the scenario. The evolution of the irradiance, it's a slight increase, but it's not very pronounced. But then the output is clearly because of the rise of temperature. So that's a fact that solar modules based on silicon, which is currently the dominant technology, are less efficient when the temperature rises. So what we see on the upper right corner is consistent with what we expected. So higher temperature, the less performant. And then for the first year yield, because we did not apply aging or any degradation factor here, it's for every year we consider that we had the first year of operation of the plant. And we see that it's more or less stable. And the understanding is that because we've got this slight rise in irradiance, it compensates somehow the decrease in performance. So then we moved to a second stage where we expanded to the 2 other locations. In that case, we restricted our work to 4 models and 2 scenarios. And in a third step, so it was kind of continuation of this analysis, but in third step, we decided to go for Spain with only data. For the 2 other locations, we received the data in a daily format that we had to process through PVSys. So very rapidly, kind of presenting the conclusion before the results. But what we noticed is that on P50, the evolution of PR was reduction for all locations, which is consistent with the expected increase in temperature everywhere. And in the case of Spain, again, with these different models and scenario, we had similar phenomenon. So the energy output is more or less stable. Meanwhile, for Senegal and Egypt, we had a decrease because, in fact, I will present it later, but both for Senegal and Egypt, the different models tend to agree on a slight decrease in the future years of the available irradiance. And on the P90, we just analyzed only for Spain, where we also got the historical data. So we compared the interannual variability of the past data with the expected interannual variability of the different models. So we will discuss that a bit further. So I won't spend too much time, but just here I picked EC3 as a model, the 2 scenarios. And you see, so on the upper part is the irradiance that's going up, the temperature that is also going up, and the evolution is more pronounced. And then when you see the output of the generation, so you see on the upper part is performance ratio going down, and the yield, well, honestly, on this specific, it seemed that the yield is slightly increasing, but I just picked one of the scenario because it was easier to understand. When we do the average of the 4 different models, we've got something which is pretty stable. So still discussing Spain, I want to show a bit the result we had for the Orly analysis. So on the upper part, the two graphs are overlapping. That's why you see only the red graph. So that was the input data. So in one case, it's the monthly values we received originally. In fact, sorry, my bad. We are talking about daily values. But then the orange graph shows the Orly data. So when you sum the annual values, they are the same, which, well, hopefully makes sense, right? We are talking about same data, but we had to check that. And then what we see is that we have similar trends. So just moving back, but we can see a difference and slightly higher performance ratio and yield when we use the daily data and we process it through PVSys. And it appears already in the global tilted irradiance, which is actually modeled by PVSys from the input data. So we might have an artifact we didn't have time, and that was not the focus of this exercise. But when we work with Orly data, we get slightly lower values, but the trend is similar. So I think the analysis is interesting. We don't see it would have been problematic if we had seen a different evolution when using higher resolution data. It's not the case. So now moving on with what we did for Senegal, so very similar to what we said before. So the yearly irradiance, as I anticipated for Senegal, the different models. So again, we are presenting here only BCCS, but the other models are more or less evolving in a similar way. So reduction of the available irradiance, temperature rise, which translates in reduction of the PR, even if here it's pretty stable, and reduction in the energy yield. Then for Egypt, similar. So I will just, aware of time, move on. And then the output, which show a similar trend. But just to put in perspective, so far it feels that we can conclude that climate change has has an impact, even if limited. But how to assess better, and in particular to put that in perspective with other factors. So if we focus one more moment on Egypt, so this would be the simulation, the evolution of the performance ratio for the first year over 30 years, taking into account the evolution of the input data. So evolution of irradiance, evolution of temperature. That's for one of the model. But as I said, for illustration, I picked only one, but the different models give very similar results. If you put that in perspective against the annual aging, so every year your module is expected to lose between 0.3 and 0.5% of efficiency. That's the normal process of aging of a solar module. So you see the blue graph is still representing what would have been the year one performance ratio. But if you combine it with this evolution, so you've got slightly less efficient system because temperature is rising, but you see that the impact of aging is way more pronounced. And then we just randomly simulated some downtime. So this is what we get here. So this gray line will include, in addition to module aging, some random downtime, considering that over 20 or even 30 years of lifetime, which is very often the time that is used for the scenario for the bank. You see that, in fact, here it appears that the impact of climate change specifically against other factors is quite limited. Then let's move on. Aware of time, I'm going to speed up. So on the P90, so you've got the graph again. What do you get between P50 and P90? A series of uncertainties. So that will be computed, and we were wondering if the interannual variability would have an impact on the P90. So here an illustration, the same as before, but with some figures. There are some realistic figures, not the exact simulation. So you get your input data, you've got your P50 yield, you apply some uncertainties, so accuracy of data, interannual variability, uncertainty on your model, as I mentioned before, and then you deduce the P90. So in specific case of the Spanish project, So we've got the interannual variability based on 1 year, variability based on 10 years. And this is what you get. So you see that there is an evolution. Potentially it could decrease, but the trend is rather to have an increase in the interannual variability, but it's also not very pronounced. So let me briefly comment on the conclusion. So I think the most important thing, and that's rather e-learning than Jupyter Notebook, to quote Nube, but that's really important. We can, I think, claim, even if it's only 3 assets we studied, that the climate change is not good news for PV. I mean, there's no good news related to climate change, not even the perspective of generating more. It seems that the impact is limited, so no particular rise expected, but also no sharp decrease so far. And as for the use of the data, all this work has been extremely interesting. It was important to use the tools we use on a daily basis in our work, but it is quite heavy, it's time consuming. So maybe if we want to have some vision of the impact of climate change, we can have very simple metrics to give an idea of potential evolution of P90 and the uncertainty. And ultimately, the reason why people are using satellite-derived data, it's because they are bankable. They've been benchmarked against ground measurements. So there would be need to have some similar work to validate those numerical weather models. Thank you for your attention. And just to recall that it's not only yield, so the impact of climate change can have very severe consequences on the assets. And
very good. Thank you, Nicola. Yes, and yeah, the impact on assets, that could be the next chapter in another case study. So there's a lot more to look into. But thank you very much. That was really enlightening in terms of how the climate data, particularly temperature and solar radiation, are used in developing new solar power plants and the finance particularly. And so now we are opening to questions and answers. We have about 10 minutes if we have enough questions. Otherwise, we can close a little sooner. There were a few questions on a couple of questions on the first presentation on use of seasonal forecast for gas demand. And just as a recap, so we had these 2 examples. We chose seasonal forecast in the first case and projections in the second. In the first case for gas demand, and the purpose is really to try to help a player, an international player like Enel, to improve the efficiency in the use of gas. So that would mean fewer emissions of greenhouse gases if we manage to use a seasonal forecast properly, given that gas is not going to go away anytime soon. And the second one is to help with the planning and development of solar power farms, and the same could apply to wind, similar considerations. In terms of questions, so I'd like to ask my colleagues, all presenters, to come to the floor with the camera on, and we'll go through the questions we had. So the first part was about some bias adjustment of seasonal forecast, and also the assessment of the seasonal forecast, why they were assessed. So we had 2 questions from Naveen Gautam, and thanks for the questions. And others, please, there is still time to ask questions, so type them quickly so we can answer them, and we'll address all of them if we can get on time. And so, yeah, Naveen was asking about the seasonal forecast, the bias adjustment. There was an answer here. Bias adjustment, yes, I think also to complement what's been written there, the specific bias adjustment in this case was the quantile mapping, as Laura also presented. And I don't know whether Laura wants to add anything more to the questions?
No, I
Or
will
Nube?
answer. I don't know if Navi
Yes.
is fine, but I should answer.
Okay. Nube,
Maybe
yes.
Nube wants something.
Yes, please.
Yes, I would like to mention, so it's not answering, I have already included some hints to this question in the question and answer, but I would like to highlight that the climate indicator that we are providing in the C3S energy service are bias adjusted. So that just in case you have some doubt regarding that. So this climate and energy indicator will be available during next year, but in any case, there will be bias adjusted.
Yes, and as also Nube mentioned in one of the answer, the seasonal forecast need to be bias adjusted in some way. There are many ways to do it, but certainly it's not recommended to use them as they come out of the box. So yeah, you should spend a bit of time to look into that or ask the experts to do it. And like Nube said, the products that are being delivered through C3S Energy will have bias adjustment in them. Then there was a question about the assessment of the results, why we're not using, I mean, in the case study, I should say, the probabilistic scores have not been used. And again, probabilistic scores will be used in C3S Energy in general, but this one was a specific application, and I don't know whether Laura or Luca wants to add any more on this.
So I just answered that for these studies, was enough to use the ensemble mean to calculate the correlation root mean square error. And also we use we need a deterministic scenario, so therefore we focus on the mean error of the physical variable. So for this reason, we're not using the probabilistic method.
Okay, and yeah, you actually have. Sorry, Laura. Yeah.
I don't know if it's clear or if it's enough to the answer.
It seems so. I think Naveen said awesome. So they seem to be happy with the answers from Laura and Nube.
Maybe,
okay,
Alberto, sorry, just to complement a little bit. So when you are using seasonal forecast for downstream application, usually if you would like to use the full ensemble with the 51 members or the number of members they have, depending on the seasonal prediction system, usually in order to assess the skill, how good the seasonal forecast is performing, you have to evaluate it with a probabilistic metric. So, but just then eventually for particular cases, you might want to look at the ensemble mean or the root mean square error, as Laura mentioned. But in general, if you would like to assess how is the skill of the any seasonal forecast, you need to do probabilistic skill scores or just a skill, metric in general.
Yeah, okay. Thank you, Nube. And just to complement that, so in the C3S Energy service, we will find three models, three systems of seasonal forecast, and each of them with 3 or 4 metrics. There should be 4 metrics of probabilistic scores. So watch this space, and all this will be provided to you soon enough. And then moving to the other question, there was one from Gregorius. From what I see, Nicola was not quite clear about the question. Also, I thought it was not clear to me, but Gregorius, if you want to expand a bit on the question or clarify, that'd be good. But I don't know, Nicola, if you want to just say a few words on your answer. Also, maybe also to integrate on that, you mentioned the degradation, and during the presentation you mentioned that there is a about 0.3% every year of degradation of the modules. Can you give us also an idea from a technological perspective, whether that's a stable statistic or is decreasing perhaps because the quality of the panels increase, or I mean, how is that moving?
I wish it were. So yes, I tried to explain. So the exercise we did was to evaluate what would be the first year generation. So that's the first graph you saw. But so we had for AG potentially of a 30-year reduction in 1%. Well, could be significant when you're dealing with million euros project. Even 1% is a lot. But then by nature, so silicon modules, but other technology are the same. It's a paradox, but if you expose your module to sunlight, it starts to deteriorate because of the light precisely. So there are different mechanisms that are making the module slowly less efficient. And yeah, the 0.3 I mentioned, 0.3 to 0.5 are generally accepted figures. Older modules might have come even with a 1% degradation. We are entering a tricky zone because it's generally what the manufacturer guarantees. But then if you want to claim the guarantee, it can be quite a headache because the manufacturer will ask you to take the modules, have them tested in a special lab. You've got uncertainty, etc. So those figures are generally accepted. We have return of experience of degradation of anywhere between 0.5 to 1% over many years. But it's true, it's based on existing modules that are older technologies. So the perspective is that in the future, and even today's modules are degrading less, but because there's a lot of pressure on price, sometimes the quality of the modules is worse than it used to be because, well, they sell for almost no money currently. So it's kind of a trade-off, you know. The cell technology is getting better, so potentially degradation is lower, but then you've got the manufacturing that sometimes is questionable. So I wish I could have a straightforward answer, but okay, considering 0.5, 0.4% is a reasonable assumption of the expected degradation of the modules.
Okay, and that's what you said. It's normally higher than what we see in the change in expected solar radiation and temperature, like you explained. But still, you know, there is, even if it's a few percent over 30 years from climate, the changes in climate, they could still be important to consider or not.
Yes, absolutely. I think that was a message. But the very first question we wanted to answer when we started this work with you, Alberto, was, again, yeah, it's disappointing, but that's reality, you know. Well, it's being hotter, so we've got more sun, so we are going to produce a lot. And also the last pictures are not pictures, but those to stress also that we focused only on the expected impact on yield. But there are so many aspects, like if your PV field is flooded regularly and you did not anticipate that, or you've got heavy storm, heavy winds, if you have to replace your modules every 2 years because of the storms, it's a real issue, and it's not directly an impact on the yield.
Very good. Okay, so moving to the other question, you also answered, but only partly, as far as I can see. So Florent Corner was asking about whether the calculation of the performance with PVCs also takes into account other components, not just the panels, like inverters. And so he's asking again, I mean, what does it include, PVCs?
Yeah, sorry, I didn't have time to respond. So in principle, PVCs is it's kind of a black box, but you input your design, expected losses, etc. The characteristic of your modules, characteristic of your inverter, the characteristic of your transformers. And so it does the conversion. So first of the irradiance with different loss factors like reflection, you know, depending on the position of the sun, the conversion is more or less efficient. You can have part of the irradiance reflected by the front glass of the modules, etc. But also, you've got the parameters of your inverters. So the question is PVCs taking into account the variation of performance of power electronics because of temperature, input voltage, current, etc.? Yes, it does. And again, to date, it has a good reputation because the way it is modeling the power electronics is acceptable. So yes, it does compute a lot of factors. In terms of aging, you can expect a bit of aging from the power electronics, but the impact on the efficiency is more that one day your inverter will stop working, while your modules will gradually, hopefully, sometimes they are a sharp decrease, but in principle, modules are steadily aging, while power electronics will stop working for some reason. We don't really see a real evolution in the performance of the conversion because your IGBTs are 5 or 10 years old and not brand new. So I hope.
Yes.
And sorry, I see temperature. Well, temperature can be very critical for power electronics because over a certain temperature, they stop working. They put in safe mode and they stop working. You've got issues that's called derating because of high temperature. It already happens in, well, south of Spain, Italy, South Africa, Chile. So when you build your assets, you may consider strategy with cooling. It's also the case for battery storage. You have to keep your power electronics at a certain temperature level. If it's heating too much, the efficiency decreases, and then just the device will stop working to avoid deterioration.
Okay, very good. Thank you, Nicola. And then we have a quick question here from Sturgis Misius. Have you seen any improvement by downscaling the CMIP6 models? I think I can answer that unless you want, Nicola, but I think, yeah, we haven't tested the original model against the downscaled model, but I would say that certainly there'll be quite a big difference because the original model is at 1 degree resolution and we downscale at 1/4 degree. So having 1 degree resolution is 2 cores for targeting a specific location. 1/4 degree is also not ideal, but still better than 1/4. So we haven't done that, but I would discourage people from using 1 degree model for a study like this. Unless you want to add anything to this, Nicola?
No,
No.
to be honest,
it's okay.
I heavily relied on you on the data you're providing.
Yes.
I don't have an opinion on that.
Okay, and then there was in principle a question for you, Nicola, Naveen Gutam, but I think probably something for me as well. And how are the CMIP6 models chosen for the case study? So here we've selected the models based on different features. There's different considerations. There is availability of certain resolutions because we need high enough temporal resolution for the models, not just for solar, but for other studies. And the spatial resolution also needs to be good, the sensitivity of the climate. And so there's various considerations, and we end up with 6 CMIP6 models that are usable for the type of service that we need to provide under C3S Energy. So unless there is any other final points from the speakers, I think we addressed all the questions. Maybe there's one last minute. I think I missed, if it's very quick responding, Nicola, I think this is for you. I think I missed the part that you explain how you choose the TMY using hourly data. Could you please tell a little bit how you do that? Does your method impact it? It's just 1 minute, very, very quick, Nicola.
Yes, very quick. Well, the TMY generation is something that is beyond the scope of this case study, but it's what we use usually, so that's why I mentioned it. In the present case, we did run every individual year and then recreated an average scenario for comparison. But we did not create, per se, TMY on the forecasted data in that case. That's something that might have to be considered. I don't know.
Wonderful. Okay, so thank you very much. So this was the agenda, wrap up and conclusion, 16:30, we are there, and we thank everybody for staying with us. Most of the people, some have left, unfortunately, but the recording will be available. And so to wrap up, I just want to show you what we've done so far. Webinar 1, Webinar 2, the climate indicators, wind and solar power, hydropower, electricity demand, and case studies. So all done since April to now. We have 1 webinar also left. There could be more if there is a request. And the next one is Q1 2025 after the data become available. So first half of 2025 with the update on global climate and energy products from the C3S. And as you said, all the webinars are recorded. You can find them here in the Climate Copernicus EU webinars. Like Nube said, you can also find them on our website, Inside Climate Service. And don't miss our upcoming webinars. So stay tuned. Before we go, I'd just like to thank again all the speakers. And so starting from Nube, Laura, Luca, and Nicola, thank you very much for great presentations, staying on time, and also all the attendees for asking questions and being with us. And last but not least, the organizer behind all this, Elena Restivo, my colleague at Inside Climate Service. You saw the webinar going very smoothly, and that's just because she's been great organizing this and keeping us on track. So thanks again, Elena, and keep also watching the space here for more products to come with the C3S Energy. Thank you very much for attending, and until next time, bye.